Picture this: 4.2 light-years away, orbiting our nearest stellar neighbor, sits a world that might harbor life. Proxima b, so close in cosmic terms, yet separated from us by a gulf so vast it renders our greatest spacecraft laughably inadequate. Despite decades of advancing technology, despite revolutionary propulsion concepts and ambitious plans, this nearest possible destination for interstellar exploration remains functionally unreachable. We will delve into why the journey to Proxima b represents one of humanity's most impossible challenges. What would crossing the void between stars truly demand? Why does the universe seem designed to keep the stars forever beyond our grasp? If you enjoy these cosmic explorations, please like and subscribe. Join us as we explore the unimaginable distances separating us from our nearest neighbor. Let's begin. "4.2 light-years. When spoken aloud, this distance to Proxima Centauri sounds almost manageable, a cosmic stone's throw in the grand scale of our galaxy. After all, we measure interstellar distances in units far vaster than this. The Milky Way stretches 100,000 light-years across. Andromeda, our nearest galactic neighbor, lies 2.5 million light-years distant. Against such incomprehensible scales, 4.2 light-years feels neighborly, intimate even, like living just down the street from someone rather than across an ocean. This numerical proximity creates a dangerous illusion in our minds. We hear nearest star and imagine something achievable, something within the realm of possibility, if we simply apply enough ingenuity and determination. The number itself betrays us, whispering promises of accessibility that the underlying reality cannot fulfill. 4.2, such a modest, human-scaled number. We drive farther than that to visit relatives. We've flown aircraft for longer continuous journeys. The digits themselves seem to invite comparison with distances we traverse routinely in our daily lives. But light-years are not kilometers. A single light-year represents the distance light travels in an entire year, moving at 300,000 kilometers per second, a velocity so extreme that nothing with mass can ever reach it. That 4.2 translates to roughly 40 trillion kilometers, or 25 trillion miles if you prefer. To put this in perspective, the distance from Earth to Neptune, the farthest planet in our solar system, is merely 4.5 billion kilometers. Proxima Centauri lies nearly 9,000 times farther than Neptune. Consider it another way. If we could shrink the distance between Earth and Proxima Centauri to the width of the continental United States, the entire solar system, from the Sun to the orbit of Neptune, would fit within the length of a single city block. Everything humanity has ever explored directly, every world we've photographed up close, every place our spacecraft have visited, exists within that single block. Proxima Centauri waits on the opposite coast, separated by thousands of miles of empty highway in this scaled-down model. The star's proximity becomes even more deceptive when we examine what surrounds us. Within that 4.2 light-year radius, only 3 stellar systems exist: Proxima Centauri itself and its binary companions Alpha Centauri A and B. Beyond this tiny bubble, the next nearest stars lie considerably farther: Barnard's star at 6 light-years, Wolf 359 at 7.8. We inhabit a relatively sparse region of our galactic neighborhood, which means our nearest neighbor represents not just the closest option, but essentially the only remotely accessible target for interstellar exploration. This deceptive proximity has shaped decades of scientific planning and popular imagination, creating a cruel paradox. The closest possible destination for humanity's first interstellar journey remains functionally unreachable with any technology we currently possess or can reasonably envision developing within the next several generations. In 2016, astronomers announced a discovery that electrified the scientific community and captured public imagination worldwide: Proxima b, an exoplanet orbiting within the habitable zone of our nearest stellar neighbor. The announcement came from the European Southern Observatory, based on years of painstaking observations using the HARP spectrograph in Chile. Scientists had detected the subtle wobble in Proxima Centauri's motion, a telltale gravitational tug caused by an orbiting planet pulling on its parent star. The discovery transformed Proxima Centauri from merely our closest stellar neighbour into something far more compelling. A system potentially harbouring a world where life might exist. The planet itself challenged many assumptions about what habitable worlds should look like. Proxima b orbits its star once every 11.2 days, circling at a distance of just 7.5 million kilometres, a fraction of Mercury's distance from our Sun. Yet this proximity doesn't condemn the planet to scorching temperatures, because Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. At that orbital distance, Proxima b receives roughly 65% of the stellar energy that Earth receives, placing it squarely within the habitable zone where liquid water could theoretically exist on a planetary surface. The mass estimates added to the intrigue. Proxima b appears to be at least 1.3 times Earth's mass, suggesting a rocky composition rather than a gas giant. This places it firmly in the category of potentially terrestrial worlds, planets with solid surfaces where chemistry could unfold in ways familiar to us. The combination of factors seemed almost too perfect. Our nearest stellar neighbour hosting a roughly Earth-sized planet in the habitable zone, the universe had placed a potentially habitable world at the closest possible location beyond our solar system. This discovery fundamentally altered the conversation about interstellar exploration. Before Proxima b, discussions of travelling to other stars remained abstract, focused on distant systems we knew possessed planets but couldn't study in detail. Kepler had revealed thousands of exoplanets, but most orbited stars hundreds or thousands of light-years away. Proxima b offered something different, a concrete target, a specific destination that combined scientific interest with relative proximity. The planet transformed interstellar travel from philosophical speculation into something resembling an actual goal, however distant. The timing proved significant as well. The discovery came amid growing technical capability in exoplanet characterization. Within years, astronomers had begun studying Proxima b's potential atmosphere, searching for signs of habitability or even biosignatures. Each new observation refined our understanding while generating new questions. Does the planet retain an atmosphere despite its star's violent flares? Is it tidally locked, with one face eternally illuminated? Could liquid water pool on its surface, or in subsurface oceans beneath a frozen crust? These questions elevated Proxima b from astronomical curiosity to existential significance. For the first time in human history, we knew of a specific world, orbiting a specific star visible to the naked eye, where the conditions for life might exist. The planet became more than a point of light in telescopic data. It became a destination, a place with genuine scientific meaning, a world that might answer the ancient question of whether life exists beyond Earth. To truly grasp why reaching Proxima b represents such an extraordinary challenge, we must first comprehend what 4.2 light-years actually means in practical terms. Light, the fastest phenomenon in the universe, travels at approximately 300,000 kilometers every single second. In 1 year, maintaining this incredible velocity without rest or deviation, light covers about 9.5 trillion kilometers. Multiply that staggering distance by 4.2, and you arrive at roughly 40 trillion kilometers, the gulf separating us from Proxima Centauri and its tantalizing planet. Human minds struggle with such numbers. We evolved to comprehend distances we could walk, see, or at most sail across. Our neural architecture simply lacks the framework for intuiting distances measured in trillions. So we resort to analogies and scaled comparisons, attempting to translate cosmic immensity into something our pattern-seeking brains can process. Imagine the Earth reduced to the size of a grain of sand. At that scale, the Moon would sit 5 millimeters away, close enough to pinch between your fingers. The Sun would be a small marble positioned 2 meters distant. Neptune, at the edge of our solar system, would rest 60 meters away, across a large room or down a hallway. And Proxima Centauri? At this same scale, with Earth as a grain of sand, our nearest stellar neighbour would be located 500 kilometers away. The distance from London to Edinburgh, from Los Angeles to San Francisco, from Paris deep into Germany. Every probe we've ever launched, every spacecraft that has carried our cameras and instruments to distant worlds, has travelled within that room or down that hallway. None have crossed even a fraction of the journey to the neighbouring city that represents Proxima Centauri. Consider velocity instead of distance. A commercial airliner cruises at roughly 900 kilometers per hour. At that speed, a flight to Proxima Centauri would require 5 billion years, longer than Earth has existed, longer than multicellular life has flourished on our planet. Even travelling at the speed of the International Space Station, which orbits Earth at 28,000 kilometers per hour, the journey would still consume over 160 million years. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of nearly 200,000 kilometers per hour during its close solar passes. Impressive by any human standard, yet at that velocity, the trip to Proxima Centauri would still require over 25,000 years. These comparisons reveal an uncomfortable truth. The distances between stars exist on a scale so divorced from human experience that our fastest machines might as well be standing still. We measure spacecraft velocities in kilometers per second, celebrating each incremental improvement in propulsion efficiency. But cosmic distances demand velocities measured in significant fractions of light speed, percentages rather than kilometers. This fundamental mismatch between our capabilities and the requirements of interstellar travel defines the central challenge. The universe has structured itself with vast emptiness between the islands of matter we call stars. And for beings who evolved on a planetary surface hoping to reach other worlds, these cosmic scales present barriers that transcend mere engineering. Voyager 1, launched in 1977, represents humanity's most distant messenger, travelling through space at 17 kilometers per second, a velocity that seems impossibly fast by terrestrial standards. That's over 61,000 kilometers per hour, fast enough to circle Earth's equator in less than 40 minutes. By any measure we use in daily life, Voyager 1 moves with staggering speed, racing through the void faster than any object humanity has ever sent into the cosmos. Yet despite nearly 5 decades of continuous travel, despite covering more distance than any other human-made object in history, Voyager 1 has barely begun to scratch the surface of interstellar space. The probe crossed into interstellar space in 2012, becoming the first human artifact to leave the heliosphere, the bubble of charged particles blown outward by our Sun. This achievement, celebrated worldwide, marked a genuine milestone in exploration. But the celebration must be tempered with perspective. Voyager 1 now sits roughly 24 billion kilometers from Earth, a distance that sounds impressive until you realize it represents merely 0.002 light-years. After 47 years of travel, the probe has covered 0.002 of a single light-year. At its current velocity, Voyager 1 would require approximately 76,000 years to cover the 4.2 light-years to Proxima Centauri, and that's assuming it were actually headed in that direction, which it isn't. The spacecraft is travelling toward the constellation Ophiuchus, nowhere near our nearest stellar neighbour. Even if we could somehow redirect it mid-flight, everyone alive today would be separated from the probe's arrival by 3,000 human generations. Civilizations would rise and fall. Our current languages would evolve into mutually unintelligible descendants. The technological society that built Voyager would be as distant to the people witnessing its arrival as the first agricultural settlements are to us. The probe carries its famous golden record, an artifact meant to introduce humanity to any intelligent beings who might one day encounter it. The record contains sounds and images from Earth, greetings in multiple languages, music spanning cultures and centuries. It's a beautiful gesture, a message in a bottle cast into the cosmic ocean. But the sobering reality is that Voyager 1 will drift through the galaxy for millions of years before even having a remote chance of passing near another star system. The vast majority of its journey will be spent in absolute emptiness. crossing the lightless void between stellar systems. Voyager's achievement shouldn't be diminished. It represents extraordinary engineering and stands as a testament to human curiosity and ambition. The data it has returned about our solar system's outer regions and the boundary of interstellar space proved invaluable. But as a demonstration of interstellar travel capability, Voyager 1 reveals just how far we remain from achieving anything resembling practical journeys to other stars. Our fastest, most distant probe, after half a century of travel, has covered a distance so small in interstellar terms that it barely registers. A sobering reminder of the immense gulf between what we've accomplished and what reaching Proxima b would require. To visit Proxima b within a single human lifetime, our spacecraft would need to achieve velocities that dwarf anything we've ever accomplished. Let's consider what within a human lifetime actually means for interstellar travel. If we're generous and assume a century, longer than most people live, but not impossibly so, we need to cover 4.2 light-years in 100 years. This requires sustained velocities of roughly 4% the speed of light, or about 12,000 kilometers per second. That's over 700 times faster than Voyager 1, our current speed record holder. But a century remains uncomfortably long for a mission timeline. The scientists and engineers who design and launch such a mission would never witness its success. The political will to fund decades-long projects with no immediate returns proves notoriously difficult to maintain. So let's be more ambitious and aim for a 50-year journey. Still longer than most careers, but short enough that some who launch the mission might live to see its arrival. Now we need velocities around 8% light speed, or 25,000 kilometers per second. We've increased the challenge substantially, requiring speeds over 1,400 times what Voyager achieves. The most optimistic scenarios imagine even faster transits. A 20-year journey to Proxima Centauri demands velocities approaching 20% light speed, 60,000 kilometers per second. At these speeds, relativistic effects begin to matter. Time dilation becomes noticeable, though not dramatic. The spacecraft experiences slightly less elapsed time than observers on Earth. But achieving such velocities requires confronting challenges that extend far beyond simply building bigger rockets or more efficient engines. Consider the energy requirements. Kinetic energy scales with the square of velocity, meaning that doubling your speed requires 4 times the energy, tripling it requires 9 times the energy, and so forth. At 20% light speed, even a small probe carries kinetic energy equivalent to thousands of nuclear weapons. All that energy must come from somewhere, either carried as fuel, gathered en route, or beamed from external sources. Each approach presents formidable obstacles. The speed requirements also create secondary problems that compound the primary challenge. At these velocities, interstellar dust and gas, normally harmless, transform into a deadly hail of projectiles. A grain of sand encountered at 20% light speed hits, with the force of an exploding grenade. Shielding becomes essential, but shielding adds mass, which requires more energy to accelerate, which demands more fuel or more powerful propulsion systems. Navigation at such speeds presents its own challenges. At 60,000 kilometers per second, you cover the distance from Earth to the Moon in just 6 seconds. Course corrections must be planned far in advance, as any deviation from the intended path compounds rapidly over interstellar distances. Communications with Earth take years, making real-time guidance impossible. The spacecraft must operate autonomously, executing a mission plan developed years or decades before launch, with no possibility of adapting to unexpected discoveries or obstacles encountered along the way. The fundamental mathematics of spaceflight, encapsulated in Tsiolkovsky's rocket equation, reveals why conventional propulsion methods fail so spectacularly for interstellar travel. Formulated over a century ago by Russian scientist Konstantin Tsiolkovsky, this elegant equation describes the relationship between a rocket's velocity change, the speed at which it expels propellant, and the ratio of its initial mass to final mass. The equation itself appears deceptively simple, but its implications for interstellar missions prove devastating. As the desired velocity increases, the required fuel grows exponentially, not linearly, but exponentially, creating demands that quickly become absurd. Consider what this means in practical terms. To achieve even modest velocity changes using chemical rockets, you need to carry fuel. But fuel has mass, which means you need more fuel to accelerate that fuel, which adds more mass, which requires even more fuel in a vicious mathematical spiral. For journeys within our solar system, this proves manageable. We can launch spacecraft to Mars or Jupiter by accepting that most of the launch mass consists of fuel, with the actual payload representing a small fraction of the total. The math works, barely, because the velocity changes required remain relatively modest. But interstellar velocities break this delicate balance completely. To reach even 1% of light speed using conventional chemical propulsion, the fuel requirements become genuinely absurd. For every single kilogram of spacecraft, you would need roughly 1,000 trillion kilograms of fuel. That's not a typographical error. 1,000 trillion kilograms per kilogram of payload. To put this in perspective, such a spacecraft would need to carry fuel masses exceeding that of entire mountains, planets, or in extreme cases, multiple Earths for even the smallest probe. The rocket equation's tyranny extends beyond chemical propulsion. Even with more efficient propulsion systems that expel mass at higher velocities, the fundamental relationship remains. You can improve the ratio, make the numbers less catastrophically large, but you cannot escape the exponential growth. Nuclear propulsion helps. Fission or fusion reactions release far more energy per unit mass than chemical reactions. Ion engines that accelerate particles to extreme velocities improve efficiency dramatically. But even these advanced systems cannot overcome the equation's fundamental constraints when targeting velocities measured in significant percentages of light speed. This mathematical barrier has driven propulsion theorists toward increasingly exotic solutions. If you cannot carry enough fuel, perhaps you collect it along the way. The Bussard ramjet concept of scooping up interstellar hydrogen. If carrying reaction mass proves impossible, perhaps you push against something else entirely. Laser sails driven by external energy sources, or solar sails utilizing photon pressure. Each approach represents an attempt to circumvent rather than overcome the rocket equation's iron logic. The equation teaches a humbling lesson. The universe imposes mathematical constraints that no amount of engineering cleverness can fully overcome. We can work around these limits, find creative alternatives, exploit loopholes in the assumptions underlying conventional rocketry. But we cannot simply build bigger rockets or more powerful engines and expect to achieve interstellar velocities through incremental improvements. Traditional rocket engines, which have carried us to the moon and throughout our solar system, burn chemical fuel to generate thrust. But for interstellar journeys, the fuel requirements become absurdly prohibitive. Chemical propulsion works through straightforward combustion reactions. Fuel and oxidizer combine, releasing energy that heats expanding gases, which then blast through a nozzle to generate thrust. This technology has powered every human journey beyond Earth's atmosphere, from the Saturn V that carried astronauts to the moon to the space shuttle that built the International Space Station. Within our solar system, chemical rockets remain our workhorse technology, proven and reliable. The problem emerges when we examine the exhaust velocities these engines can achieve. The fastest chemical rockets expel their propellant at around 4 to 5 kilometers per second. Impressive compared to the speed of sound, but utterly inadequate for interstellar requirements. Remember that we need final spacecraft velocities of thousands or tens of thousands of kilometers per second. When your exhaust velocity is measured in single-digit kilometers per second, reaching final velocities thousands of times higher requires fuel mass ratios that defy comprehension. The numbers become genuinely absurd. To accelerate even a tiny probe to just 1% of light speed, 3,000 kilometers per second, using chemical propulsion would require a fuel-to-payload mass ratio of approximately 1 quintillion to 1. That means for every single kilogram of spacecraft, you would need 1 billion kilograms of fuel. To put this in perspective, Earth itself has a mass of roughly 6 billion trillion kilograms. Your fuel supply would need to mass hundreds of times more than our entire planet, to propel a 1 kilogram probe to a velocity that would still take over 400 years to reach Proxima Centauri. Even if we somehow solved the fuel storage problem, the logistics of such a mission would prove impossible. Where would you obtain this fuel? Earth's entire mass, converted entirely to rocket propellant, couldn't supply enough for a meaningful payload. You couldn't manufacture it, mine it, or gather it from anywhere in the solar system. The fuel requirements exceed the available material resources not just of Earth, but of multiple planetary systems combined. These calculations aren't theoretical speculation. They emerge directly from the well-understood physics of chemical reactions and rocket propulsion. Chemical bonds between atoms can release only so much energy per unit mass. This places hard limits on exhaust velocities, which in turn constrains achievable spacecraft velocities through the rocket equation's unforgiving mathematics. No breakthrough in fuel chemistry, no advancement in engine design, no clever engineering can circumvent these fundamental thermodynamic constraints. This is why chemical propulsion effectively ends its usefulness beyond our solar system. The technology that carried us to the Moon, that enabled our exploration of Mars and the outer planets, that remains our primary means of reaching orbit, simply cannot scale to interstellar requirements. The gap between what chemical rockets can do and what interstellar missions demand isn't a matter of incremental improvement. It represents a chasm requiring entirely different approaches to propulsion. One of the first concessions we must make in contemplating interstellar travel is perhaps the most difficult: accepting that humans cannot make this journey. This realization cuts against every instinct embedded in our exploration narratives. We imagine astronauts planting flags on distant worlds, human eyes witnessing alien sunrises, boots leaving the first prints in extraterrestrial soil. These images populate our science fiction, inspire our space programs, and drive public enthusiasm for exploration. Yet the physics of interstellar travel makes crewed missions vastly more difficult than robotic ones. Perhaps impossibly so. Human beings require an elaborate support infrastructure to survive. We need breathable air, drinkable water, edible food, protection from radiation, comfortable temperatures, and waste recycling systems. A human-rated spacecraft must carry or generate all these resources for the entire journey duration. For a 50-year mission, even with perfect recycling, the life support mass adds up dramatically. Water alone, essential for drinking, hygiene, and cooling systems, weighs roughly 2 kilograms per person per day. Food, even in concentrated form, adds more mass. The habitable volume must be large enough to prevent psychological deterioration during decades of confinement. Then there's radiation shielding. In interstellar space, far from any star's protective magnetosphere, cosmic rays bombard everything continuously. These high-energy particles can damage DNA, increase cancer risk, and degrade electronics. Effective shielding requires substantial mass, typically meters of water, polyethylene or other hydrogen-rich materials surrounding the crew compartment. This shielding alone might weigh hundreds of tons, all of which must be accelerated to interstellar velocities and then decelerated at the destination. Compare this to a robotic probe. Machines don't need air, water, or food. They tolerate temperature extremes and radiation doses that would kill humans instantly. They don't suffer psychological stress from isolation or confinement. A robotic spacecraft can be tiny, perhaps weighing mere grams in the most extreme designs, while still carrying cameras, spectrometers, and communication equipment. The mass difference between a human-rated interstellar ship and a miniaturized probe might span 8 or 9 orders of magnitude. When mass directly translates to energy requirements through the rocket equation, this difference becomes decisive. The journey duration creates additional problems for human crews. Even at 20% light speed, the trip requires 20 years, long enough for significant aging, potential health complications, and crew psychology challenges. Slower missions might span lifetimes, requiring either suspended animation technologies we don't possess, or generation ships where children born en route would complete missions their grandparents started. Both scenarios introduce complexities that dwarf the already formidable engineering challenges. This isn't defeatism but pragmatism. Robotic exploration doesn't represent humanity's failure to reach the stars. It represents our intelligence in recognizing that machines can serve as our eyes, hands, and instruments across distances our bodies cannot traverse. The rovers exploring Mars are no less achievements of human exploration for being remotely operated. Similarly, probes reaching Proxima b would represent genuine human accomplishment, even without carrying human passengers. The discovery, the knowledge gained, the expansion of our cosmic perspective, these remain fundamentally human endeavors, regardless of whether flesh or silicon makes the actual journey. Ion engines represent a significant advancement over chemical rockets, using electric fields to accelerate ions and generate thrust with remarkable efficiency. Rather than burning chemical fuel, ion drives ionize a propellant, typically xenon gas, stripping electrons from atoms to create charged particles. These ions then pass through electric grids that accelerate them to extremely high velocities before expelling them as exhaust. The expelled ions leave at speeds 10 times higher than chemical rocket exhaust, sometimes exceeding 40 kilometers per second. This dramatic increase in exhaust velocity translates directly to improved fuel efficiency through the rocket equation. The technology has proven itself in actual missions. NASA's Dawn spacecraft used ion propulsion to visit both the asteroid Vesta and the dwarf planet Ceres, becoming the first spacecraft to orbit two extraterrestrial bodies. The European Space Agency's Smart 1 mission used ion drives to reach the Moon. Japan's Hayabusa probes employed ion engines for their asteroid sample return missions. These successes demonstrate that ion propulsion isn't theoretical speculation but mature, flight-proven technology that works reliably in the harsh environment of space. The efficiency gains come with a significant trade-off: thrust. Ion engines produce incredibly weak thrust, often measured in millinewtons, roughly equivalent to the weight of a few coins pressing on your hand. Dawn's ion engine, operating at full power, generated thrust comparable to the weight of a single sheet of paper. This means acceleration occurs gradually, requiring weeks or months of continuous operation to achieve meaningful velocity changes. For missions within the solar system, this proves acceptable. You can afford to accelerate slowly when you're not fighting against planetary gravity and have years to reach your destination. But for interstellar missions, even ion propulsion's improved efficiency falls dramatically short. The exhaust velocities, while 10 times better than chemical rockets, remain far too low for achieving the relativistic speeds interstellar travel demands. To reach even 1% of light speed using ion drives would still require fuel masses thousands of times greater than the spacecraft itself. The mission duration stretches into geological timescales. Calculations suggest an ion-propelled mission to Proxima Centauri would require over 40,000 years, better than chemical propulsion's million-year timescales, but still hopelessly impractical. The power requirements create additional challenges. Ion engines need electrical power to ionize propellant and maintain the accelerating electric fields. This power typically comes from solar panels near the Sun or radioisotope thermoelectric generators for missions venturing into the outer solar system. For interstellar missions, solar power becomes useless once you move beyond the inner solar system, and current radioisotope generators can't provide sufficient power for the thrust levels needed. Nuclear reactors could theoretically supply enough power, but adding a reactor increases spacecraft mass, which reduces the benefit of the efficient propulsion. Ion propulsion represents genuine progress in spacecraft propulsion technology, expanding our capabilities within the solar system and enabling missions that would prove difficult or impossible with chemical rockets alone. But as a path to the stars, ion engines demonstrate how even dramatic improvements over conventional technology remain inadequate when confronting interstellar distances. Nuclear thermal rockets offer another incremental improvement, using nuclear reactors to superheat propellant to extreme temperatures before expelling it at high velocity. The concept is conceptually straightforward. A nuclear reactor generates immense heat through fission reactions, and this thermal energy transfers to a propellant, typically liquid hydrogen, which expands rapidly and exhausts through a nozzle. The nuclear heat source can achieve far higher temperatures than chemical combustion, allowing exhaust velocities roughly double those of conventional chemical rockets. This improvement translates to better fuel efficiency and reduced propellant requirements for any given mission. NASA extensively tested nuclear thermal rocket technology during the 1960s and early 1970s under programs like NERVA, the nuclear engine for rocket vehicle application. These tests demonstrated that the technology works, that reactors can operate reliably in rocket configurations, and that the predicted performance gains are achievable. Engine tests successfully produce thrust while maintaining reactor stability and controlling the extreme temperatures involved. The program ended not because of technical failures, but due to budget constraints and shifting political priorities as the Apollo program wound down. Modern interest in nuclear thermal propulsion has resurged, particularly for Mars missions where the improved efficiency could reduce transit times and payload mass. The technology offers genuine advantages over chemical rockets for deep space exploration within our solar system. A nuclear thermal rocket could potentially cut Mars journey times from 9 months to 4 or 5 months, reducing crew radiation exposure and psychological stress. For missions to the outer planets, the improved efficiency means more scientific instruments and less propellant mass. Yet for interstellar missions, even nuclear thermal propulsion proves grossly inadequate. The exhaust velocities, while impressive compared to chemical rockets, still reach only about 9 kilometers per second, far below the thousands of kilometers per second required for reasonable interstellar transit times. Applying the rocket equation to interstellar velocities reveals that nuclear thermal propulsion would still require fuel masses millions of times greater than the spacecraft payload. Mission durations would stretch beyond 40,000 years to reach Proxima Centauri, improved over chemical propulsion but still spanning timescales longer than recorded human history. The reactor mass creates additional problems. Nuclear reactors require shielding to protect both equipment and any crew from radiation. They need cooling systems to prevent meltdown. The fuel elements must withstand extreme temperatures without failing. All this infrastructure adds mass that must be accelerated along with the payload. For missions within the solar system, this mass penalty remains acceptable because the performance gains outweigh the added weight. For interstellar missions requiring enormous velocity changes, the reactor's mass becomes a significant burden that partially negates the efficiency improvements. Nuclear thermal propulsion represents meaningful progress in rocket technology, potentially enabling faster and more efficient exploration of our solar system. But like ion engines and other advanced propulsion concepts, it demonstrates that even substantial improvements over chemical rockets leave us nowhere near the capabilities interstellar travel demands. The gap between our best nuclear thermal designs and the requirements for reaching Proxima b within human-relevant timescales remains vast. The variable-specific impulse magnetoplasma rocket, developed by former astronaut Franklin Chang Diaz, represents one of the most sophisticated plasma propulsion systems ever designed. VASMIR uses radio waves to heat gas, typically argon or hydrogen, to plasma temperatures exceeding 10,000 degrees. Powerful electromagnets then confine and direct this superheated plasma, channeling it out the back of the engine to produce thrust. The innovation lies in its variable configuration. Operators can adjust the system to produce either high thrust with lower efficiency or low thrust with exceptional efficiency, adapting to different mission phases. The technology has undergone extensive ground testing at Ad Astra Rocket Company's facilities in Texas. Test firings have demonstrated stable plasma generation, magnetic containment, and thrust production matching theoretical predictions. The engine operates for extended periods without degradation, suggesting it could function reliably during long-duration missions. NASA has expressed interest in VASMIR for potential Mars missions, recognizing that the engine's efficiency could dramatically reduce transit times compared to conventional propulsion. The performance numbers seem impressive at first glance. With sufficient onboard power, VASMIR could theoretically accelerate a spacecraft continuously, building up velocity gradually but persistently. Proponents suggest it might reduce a Mars journey from 18 months to just 39 days, a dramatic improvement that would minimize crew radiation exposure and reduce the psychological burden of long-duration spaceflight. For exploring the outer solar system, Vasmir offers similar advantages, enabling faster missions with reduced propellant mass. Yet even this sophisticated plasma engine falls hopelessly short for interstellar applications. Despite its advantages over chemical and nuclear thermal propulsion, Vasmir would still require roughly 2,200 years to reach Proxima Centauri. The fundamental limitation remains exhaust velocity. While Vasmir can achieve higher exhaust speeds than nuclear thermal rockets, it still operates far below the velocities needed for interstellar transit. The engine also requires enormous electrical power, tens or hundreds of megawatts for meaningful thrust levels, power that would need to come from onboard nuclear reactors, adding substantial mass to the spacecraft. The power-to-thrust ratio presents another challenge. Vasmir is essentially an electric propulsion system, converting electrical energy into kinetic energy of expelled plasma. This conversion process, while efficient by rocket standards, still wastes significant energy as heat that must be radiated away. For the high power levels needed to generate useful thrust, the radiator systems alone might weigh many tons. And all this mass, the reactor, the radiators, the plasma generation equipment, must be accelerated along with the payload. Vasmir represents cutting-edge propulsion technology and may well revolutionize exploration within our solar system. But as a solution for reaching other stars, even this advanced system barely improves upon technologies developed decades earlier. The 2,200-year transit time to Proxima Centauri, while better than earlier estimates, still spans a period longer than all of recorded Western civilization. Vasmir teaches us that even dramatic technological leaps forward leave us firmly bound to our solar system, unable to bridge the vast gulf to even our nearest stellar neighbor. Perhaps no propulsion concept sounds more audacious than Project Orion, the idea of propelling a spacecraft through space by detonating nuclear bombs behind it. The concept emerged in the late 1950s at Los Alamos National Laboratory, where scientists including Freeman Dyson and Ted Taylor worked out the mathematics and engineering of nuclear pulse propulsion. The basic design called for a massive spacecraft with an enormous steel pusher plate mounted on shock absorbers. Nuclear bombs would be ejected behind the craft at regular intervals, detonating several dozen meters away. The explosion's energy would strike the pusher plate, and the shock absorbers would convert this violent impact into smooth forward acceleration. The idea seems insane at first encounter. Riding a continuous series of nuclear explosions sounds like science fiction at its most reckless. Yet, the physics proved sound. Controlled tests using conventional explosives demonstrated that the pusher plate concept worked. Engineers calculated that such a system could achieve exhaust velocities far exceeding chemical rockets, potentially reaching several % of light speed if fusion bombs replaced fission devices. The project attracted serious attention and funding through the early 1960s, with detailed engineering studies producing surprisingly practical designs. The spacecraft envisioned in these studies would be enormous, perhaps 400,000 tons with a pusher plate 100 meters in diameter. This massive structure would need to withstand repeated nuclear detonations, requiring robust construction unlike any spacecraft built before or since. The design called for launching roughly 300,000 nuclear devices, ejecting and detonating them in sequence over months or years of continuous acceleration. Each explosion would add a small velocity increment, gradually building up to the tremendous speeds needed for interstellar travel. With fusion bombs rather than fission devices, Project Orion theoretically could propel a spacecraft to Proxima Centauri in approximately 150 years. This represents genuine progress, a mission duration that, while still spanning multiple human lifetimes, begins to approach the realm of possibility. A generation ship using Orion propulsion could feasibly complete the journey, with children and grandchildren of the original crew eventually arriving at the destination. The concept sparked serious discussions about multi-generational spacecraft and the social structures needed to maintain such vessels across centuries. But numerous obstacles prevented Orion from ever launching. The partial nuclear test ban, Treaty of 1963, prohibited nuclear explosions in space, effectively ending the project's legal viability. The environmental concerns about launching a nuclear bomb-laden spacecraft from Earth's surface proved insurmountable. The sheer cost of building such a massive vehicle and producing hundreds of thousands of nuclear devices would strain even superpowers' budgets. The political optics of launching nuclear weapons into space, even for peaceful exploration, proved unacceptable during the Cold War era. Beyond these practical barriers, even Orion's impressive performance falls short of making interstellar travel routine. 150 years remains an extraordinarily long time, longer than the United States has existed as a nation, longer than the Industrial Revolution. The engineering challenges of maintaining a spacecraft and supporting a human population across such timescales introduce complexities that may prove as difficult as the propulsion problem itself. If we cannot reach Proxima b within a single lifetime, perhaps the solution lies in accepting journeys that span multiple human generations. The generation ship concept proposes launching a self-contained habitat carrying hundreds or thousands of people on journeys lasting centuries. The original crew would live out their lives aboard the vessel, raise children who never knew Earth, and those children would in turn raise another generation, continuing the cycle until distant descendants finally arrived at the destination star system. These descendants would complete a mission their ancestors initiated, reaping rewards from sacrifices made generations before their birth. The concept carries a romantic appeal, humanity spreading across the stars through dedication, spanning centuries, families united by a shared purpose greater than any individual lifetime. Science fiction has explored generation ships extensively, imagining the cultures that might develop aboard these isolated worldlets, the social structures needed to maintain cohesion across generations, and the philosophical questions about purpose and identity that would inevitably arise. These narratives capture something fundamentally human about multi-generational projects, cathedrals that took centuries to build, family businesses passed down through generations, traditions maintained across cultural continuity. But the engineering realities of generation ships introduce challenges that may prove insurmountable. The vessel must maintain a complete closed-loop life support system for centuries without failure. Every molecule of water, every breath of air, every nutrient in every meal must be recycled with near-perfect efficiency. Even tiny losses compound over generations. A failure rate of just 1% per year means total system collapse within a century. No technology we've ever built maintains such reliability over such timescales. The habitat must provide everything a human population needs, not just survival, but quality of life sufficient to maintain psychological health and social stability across generations of enforced confinement. This means agricultural systems to grow food, manufacturing capability to repair or replace broken equipment, medical facilities to handle everything from routine care to emergency surgery, educational infrastructure to transmit knowledge across generations, and recreational spaces to prevent the psychological deterioration that comes from permanent confinement. The complexity approaches that of maintaining a small town, except this town must function perfectly in the hostile environment of deep space, with no possibility of external assistance. Population genetics creates additional concerns. A small founding population risks genetic bottlenecks and inbreeding depression over multiple generations. Geneticists suggest a minimum viable population of several hundred individuals to maintain genetic diversity, but supporting hundreds of people for centuries multiplies the life support requirements and habitat mass proportionally. Some have proposed frozen genetic material, embryos or gametes stored for later use to inject genetic diversity, but this introduces complex ethical questions about creating children from stored genetic material generations after the donor's deaths. The social challenges may prove even more daunting than the technical ones. How do you maintain mission cohesion when no one alive remembers Earth or the original purpose? What prevents social fragmentation, religious schisms, or political upheaval in an isolated society with no external authority? How do you preserve technical knowledge across generations when the intermediate generations see no immediate benefit from the journey? These questions touch on fundamental aspects of human nature and social organization that no amount of engineering can fully resolve. Unlike the romantic notion of sails catching stellar winds, solar sails actually work through radiation pressure, the physical momentum carried by photons of light. Though photons have no mass, they do carry momentum, and when they strike a reflective surface, they transfer that momentum just as a thrown ball transfers momentum when it bounces off a wall. The pressure is incredibly weak. Sunlight at Earth's distance exerts a force of only about 9 micronewtons per square meter, roughly equivalent to the weight of a single grain of sand spread across an entire square meter. But in the vacuum of space, with no friction to overcome, even this gentle pressure can gradually accelerate a spacecraft over time. The concept dates back centuries. Johannes Kepler speculated about light pressure pushing comet tails in the 1600s. But practical solar sail technology has only recently become feasible. The sail must be extraordinarily thin and lightweight to maximize the area-to-mass ratio, yet strong enough to survive deployment and maintain structural integrity. Modern designs use materials mere microns thick, thinner than a human hair, made from reflective polymers or ultra-thin aluminum. These gossamer structures fold compactly for launch, then unfurl in space to span areas measured in hundreds or thousands of square meters. Japan's Icaros spacecraft, launched in 2010, successfully demonstrated solar sailing by traveling from Earth to Venus, using only light pressure for propulsion. The mission proved that the technology works in practice, not just theory. The sail deployed successfully, maintained its shape, and provided measurable thrust that gradually altered the spacecraft's trajectory. This represented a genuine milestone, the first spacecraft to journey between planets using sunlight as its sole propulsion source after escaping Earth's gravity. Yet, for interstellar missions, solar sails face severe limitations. The radiation pressure drops off with the square of the distance from the Sun. By the time a solar sail spacecraft reaches Jupiter's orbit, sunlight has weakened to just 4% of its intensity at Earth. In the outer solar system, the pressure becomes negligible. Beyond the heliopause, in true interstellar space, solar radiation provides essentially no propulsion at all. Any velocity gained must come from acceleration near the Sun, where radiation remains intense. This constraint demands that solar sails accelerate close to the Sun, diving deep into the inner solar system where temperatures soar into the thousands of degrees. The sail material must withstand this inferno without melting, warping, or losing reflectivity. Even materials chosen for their heat resistance struggle at these temperatures. The spacecraft itself requires thermal shielding to prevent its electronics and instruments from being destroyed by proximity to the Sun. Even under optimal conditions, enormous sail area, minimal spacecraft mass, acceleration trajectory passing as close to the Sun as materials can tolerate, transit times to Proxima Centauri would still stretch between 1,000 and 2,000 years. Solar sails alone cannot solve the interstellar travel problem. Japan's Icaros spacecraft demonstrated that solar sailing isn't merely theoretical, these gossamer structures can actually propel vehicles through space. Launched in May 2010 as a companion payload to the Akatsuki Venus probe, Icaros, which stands for Interplanetary Kite Craft Accelerated by Radiation of the Sun, carried a 14-meter diagonal square sail made of polyimide film just 7.5 microns thick. This membrane, thinner than a human hair, was coated with aluminum on one side to reflect sunlight and studded with thin-film solar cells to generate electrical power. The entire sail assembly weighed only 315 kilograms, including the spacecraft bus. The deployment alone represented a significant technical achievement. The sail remained folded during launch, then slowly unfurled in space through centrifugal force as the spacecraft spun. This spin deployment method allowed the gossamer membrane to stretch taut without requiring complex mechanical structures that would add weight and failure points. Cameras mounted on the spacecraft captured images of the sail fully extended against the backdrop of space. Shimmering squares of reflective material catching sunlight millions of kilometers from Earth. More importantly, Icaros successfully demonstrated measurable acceleration from solar radiation pressure. Instruments aboard the spacecraft detected velocity changes, consistent with photon momentum transfer. The mission team confirmed that sunlight alone was propelling the craft, gradually altering its trajectory toward Venus. This wasn't theoretical anymore. It was happening, observable and measurable. The spacecraft reached Venus's vicinity in December 2010, having traveled the distance using primarily solar sail propulsion after its initial launch trajectory. The mission also tested attitude control using the sail itself, by adjusting the reflectivity of different sail sections using liquid crystal panels embedded in the membrane. Engineers could create differential forces that rotated the spacecraft without expending propellant. This demonstrated that solar sails could provide not just propulsion but also maneuvering capability, addressing concerns about how such spacecraft could navigate or maintain proper orientation during long journeys. Icaros proved that solar sailing works in practice, validating decades of theoretical work and small-scale experiments. The success inspired subsequent missions. NASA's NanoSail D2 deployed a small sail in Earth orbit in 2011. The Planetary Society's LightSail 2, launched in 2019, demonstrated controlled solar sailing in Earth orbit, raising its orbit using only sunlight. These missions collectively moved solar sailing from speculative technology to proven capability. Yet, proving the concept and solving interstellar travel remain vastly different challenges. Icaros operated relatively close to the Sun, where radiation pressure remained strong, and it traveled distances measured in millions of kilometers rather than trillions. The spacecraft's modest velocity changes, celebrated as proof of concept, fall far short of what interstellar missions require. The mission demonstrated that solar sails work, but also revealed how much development remains before they could contribute meaningfully to interstellar exploration. The gap between a successful Venus flyby mission and crossing light years of space spans orders of magnitude in scale, duration, and technical complexity. For a solar sail to accelerate a spacecraft to truly high velocities, it must be deployed extremely close to the Sun, where radiation intensity reaches its peak. The relationship between distance and radiation follows an inverse square law: halve the distance to the Sun and radiation intensity quadruples. To maximize acceleration, solar sail mission designers propose trajectories that pass within just a few million kilometers of the solar surface, far closer than any planet orbits. At these distances, radiation intensity becomes thousands of times stronger than at Earth's orbit, creating thermal environments that challenge even the most advanced material science. The temperatures involved are staggering. At a distance of 4 solar radii, roughly 3 million kilometers from the Sun's center, a solar sail would experience temperatures exceeding 2,000 degrees Celsius. This approaches the melting point of many metals and far exceeds what most polymers can withstand. The sail material must not only survive these temperatures, but maintain its structural integrity and reflective properties. Any warping, buckling, or loss of reflectivity dramatically reduces propulsion efficiency. Material selection becomes critically important. Traditional polymer films, even those designed for space applications, decompose at such temperatures. Aluminum coatings can lose reflectivity or sublime directly from solid to gas. Engineers have investigated exotic materials like carbon fiber composites, ceramic films, and metal alloys specifically chosen for their thermal properties. Some designs propose using the sail's spin to create centrifugal tension that helps maintain flatness despite thermal stresses. The spacecraft attached to the sail faces even greater challenges. While the sail itself is designed to reflect most incoming radiation, some energy inevitably transfers as heat. The spacecraft bus must be shielded from this thermal onslaught while remaining lightweight enough not to negate the sail's propulsion advantage. Electronics, batteries, communication systems, and scientific instruments all have maximum operating temperatures far below what the near-solar environment delivers. Thermal protection systems add mass, insulation, heat shields, radiators to dump excess heat. The close solar approach also limits the time available for acceleration. A spacecraft cannot loiter near the Sun. It passes through perihelion in hours or days, then continues outward on its trajectory. This means all the acceleration from intense solar radiation occurs in a brief window. The sail must deploy properly, orient correctly, and survive the thermal environment during this critical phase. Any failure during the solar flyby wastes the entire mission. Some proposed designs attempt to mitigate these challenges through innovative approaches. One concept envisions manufacturing the sail from materials that intentionally ablate, their surface layers evaporating in the intense heat while the remaining material continues functioning. Another proposes sails with multiple layers that can be jettisoned once damaged. But each solution introduces new complexities and potential failure modes, demonstrating how the thermal environment near the Sun creates cascading engineering challenges that compound the already formidable task of interstellar propulsion. Combining solar sail technology with nuclear pulse propulsion, the Medusa concept envisions a spacecraft pushed forward by controlled nuclear explosions, captured by an enormous parachute-like structure. Developed in the 1990s by John Del Solom at Los Alamos National Laboratory, Medusa inverts the traditional Project Orion design. Instead of a heavy pusher plate at the rear of the spacecraft absorbing nuclear blasts, Medusa places an enormous lightweight sail ahead of the craft, tethered by cables. Nuclear charges detonate between the sail and the spacecraft, and the expanding plasma from each explosion pushes against the sail's surface. The tethers transfer this force to the spacecraft while also serving as shock absorbers to smooth the pulsed acceleration. The design offers several advantages over conventional Orion. The sail can be much lighter than Orion's massive steel pusher plate, because it doesn't need to withstand direct contact with nuclear fireballs. The explosions occur at a distance, and the sail only catches the expanding radiation and plasma. This mass savings translates directly to better performance through the rocket equation. The larger sail area also captures more of each explosion's energy, improving propulsion efficiency. The spacecraft itself sits safely behind the sail, protected from direct radiation exposure by the membrane itself. The explosions would occur in carefully choreographed sequence. Small nuclear devices, each perhaps the size of a soda can, would be released ahead of the spacecraft and detonated at precise distances and timing. The sail, potentially hundreds of meters in diameter, would catch the expanding sphere of plasma and radiation from each blast. The force would pull the spacecraft forward through the tethers, with each explosion adding velocity incrementally. Thousands of such detonations might occur during the acceleration phase, gradually building the spacecraft's velocity to a significant fraction of light speed. Performance estimates for Medusa suggest it could achieve velocities around 3% of light speed with fusion explosions, potentially reaching Proxima Centauri in roughly 140 years. This falls into the realm of generation ship timescales, long but conceivably manageable with multi-generational crews or advanced suspended animation technologies. The concept could theoretically even support follow-on missions to other nearby stars like Alpha Centauri A and B after studying Proxima Centauri, using remaining nuclear fuel to continue the journey. But Medusa faces formidable obstacles beyond the technical challenges. The political and environmental concerns that killed Project Orion apply equally here. Launching thousands of nuclear devices into space raises proliferation concerns and environmental fears. The engineering complexity of deploying and maintaining a massive sail connected by kilometers-long tethers in the radiation-intense environment behind sequential nuclear explosions pushes material science to its limits. The sail must survive repeated exposure to nuclear radiation and plasma without degrading or losing structural integrity. Most fundamentally, even Medusa's impressive performance leaves transit times measured in centuries. The concept represents genuine innovation in propulsion design, but still cannot overcome the fundamental barrier of interstellar distances. A 140-year journey remains far beyond current mission planning capabilities, requiring either generation ships or technological breakthroughs in life extension or suspended animation that remain firmly in the realm of speculation. Rather than relying on the sun's diffuse radiation, laser sails propose using concentrated beams of laser light to push spacecraft to unprecedented velocities. The concept addresses solar sailing's fundamental limitation. Sunlight weakens rapidly with distance from the sun, providing propulsion only during the initial phase of an interstellar journey. Laser systems, by contrast, can deliver focused energy across vast distances, potentially accelerating spacecraft continuously over months or years rather than hours or days. The beam remains concentrated and powerful far beyond where sunlight fades to uselessness, extending the acceleration phase and enabling dramatically higher final velocities. The physics remains similar to solar sailing. Photons carry momentum, and when laser light reflects off a sail, momentum transfers to the spacecraft. But lasers offer crucial advantages over sunlight. The monochromatic, coherent nature of laser light allows it to be focused into narrow beams that spread minimally across interstellar distances. Specialized sail materials can be optimized for the specific wavelength of the laser, maximizing reflectivity and minimizing absorption. Most importantly, the laser array's power output can be scaled to mission requirements, limited only by available energy and engineering capabilities, rather than the fixed output of the sun. The proposed systems would be enormous. A laser array powerful enough to propel spacecraft to relativistic speeds might span hundreds of square kilometers, either positioned in Earth orbit, on the lunar surface, or at gravitationally stable Lagrange points. Individual laser elements would combine their beams coherently, creating a single focused shaft of light aimed with extraordinary precision at the receding spacecraft. The power requirements stretch into gigawatts, equivalent to multiple nuclear power plants operating continuously. Beam divergence creates significant challenges. Even perfectly focused laser beams spread gradually over interstellar distances due to fundamental diffraction limits. By the time the beam reaches a spacecraft several light-years away, it might have spread across millions of kilometers despite starting mere meters wide. This dilution reduces the intensity and therefore the thrust delivered to the sail. Larger apertures on the laser array help reduce spreading, but they require even more ambitious construction projects. Targeting precision must be extraordinary. The laser must track a spacecraft moving at significant fractions of light speed across distances measured in trillions of kilometers. Any pointing error means the beam misses the sail entirely, wasting precious energy and leaving the spacecraft without propulsion. The spacecraft's position must be known to within meters across light-years of distance, requiring navigation and tracking capabilities far beyond current systems. Despite these formidable challenges, laser sail technology offers perhaps the most promising path to achieving interstellar velocities within human-relevant timescales. Theoretical calculations suggest that a sufficiently powerful laser array could accelerate small spacecraft to 20% of light speed, enabling transit times to Proxima Centauri of just 20 to 30 years. This transforms interstellar exploration from multi-generational endeavor to something achievable within a single human lifetime, or at least within the professional lifetime of the scientists and engineers who design the mission. The technology demands enormous infrastructure investment and engineering breakthroughs, but unlike some propulsion concepts, it doesn't violate known physics or require materials with impossible properties. Building a laser system powerful enough to propel spacecraft to relativistic speeds requires infrastructure on a scale humanity has never attempted. Consider the baseline requirements. To accelerate a small spacecraft to 20% of light speed, within a reasonable time frame demands laser power measured in tens of gigawatts, roughly equivalent to the output of 20 to 30 nuclear power plants operating simultaneously. This power must be converted to coherent laser light with high efficiency, focused with extraordinary precision, and directed at a target growing more distant every second. The engineering challenges multiply at every level, from power generation, through beam control, to the physical structure supporting the entire system. The laser array itself would span enormous areas. Individual laser elements, perhaps thousands or tens of thousands of them, would need to be arranged across hundreds of square kilometers to achieve the necessary aperture size for minimal beam divergence. These elements must operate in perfect synchronization, their beams combining coherently to form a single focused shaft of light. Any misalignment between elements, even by fractions of a wavelength, degrades beam quality and wastes power. Maintaining this precision across such vast distances in the thermal variations of space or the structural flexing of lunar installations, presents extraordinary control challenges. Location becomes a critical decision. Earth orbit offers accessibility for construction and maintenance, but orbital stations experience thermal cycling as they pass through sunlight and shadow, causing expansion and contraction that disrupts alignment. The Moon's surface provides stable mounting, but lunar dust poses contamination risks for optical systems, and the Moon's slow rotation complicates continuous tracking of departing spacecraft. Lagrange points offer gravitational stability but sit far from easy resupply or repair. Power generation at the required scale demands its own massive infrastructure. Solar panels spanning square kilometers might provide power in space-based installations. But even at perfect efficiency, capturing tens of gigawatts requires enormous collection areas. Nuclear reactors offer higher power density but introduce thermal management challenges. The waste heat from reactors operating at these power levels must be radiated into space using massive radiator arrays. Either approach requires construction projects dwarfing anything humanity has built beyond Earth. Cooling the lasers themselves presents another substantial challenge. Converting electrical power to laser light generates considerable waste heat, and high-power laser systems require active cooling to prevent damage. In space, heat can only be rejected through thermal radiation, requiring large radiator surfaces. The radiators, power generation equipment, structural elements, and laser optics collectively mass thousands or tens of thousands of tons, all of which must be launched from Earth or manufactured from lunar or asteroid materials, using industrial capabilities we don't yet possess. The cost estimates prove staggering. Conservative projections suggest tens of billions of dollars for even modest laser arrays, with more ambitious systems potentially requiring hundreds of billions. This approaches the cost of major national infrastructure projects. Entire highway systems, lunar bases, or large-scale renewable energy build-outs. Maintaining political and financial support for such projects across the decades of construction poses challenges potentially as difficult as the engineering itself. The infrastructure requirements for laser sail technology, while theoretically achievable, demand coordinated effort and sustained investment on a scale that tests the limits of international cooperation and long-term planning. Project Breakthrough Starshot represents the transition from theoretical speculation to actual engineering plans, backed by significant funding and coordinated scientific effort. Announced in 2016 by the Breakthrough Initiatives, a program funded by investor Yuri Milner and supported by prominent scientists including Stephen Hawking, Starshot aims to send ultralight spacecraft to the Alpha Centauri system within a generation. The project allocated $100 million for initial research and development, with plans for potentially billions more if the concept proves viable. This represents the first serious attempt to move interstellar exploration from academic papers and conference presentations into actual hardware development and mission planning. The project assembled a distinguished advisory committee, including leading physicists, engineers, and astronomers. This wasn't a fringe endeavor pursued by enthusiasts on limited budgets. It brought together expertise from particle physics, materials science, laser technology, spacecraft design, and astrophysics. The involvement of respected scientists lent credibility and attracted attention from major research institutions worldwide. Universities and laboratories began dedicating resources to solving specific technical challenges identified by the project, creating a distributed research effort spanning multiple countries and disciplines. Starshot's approach differs fundamentally from previous interstellar mission concepts. Rather than proposing massive spacecraft requiring revolutionary new propulsion systems, the project embraces miniaturization. The core insight recognizes that reducing spacecraft mass by orders of magnitude makes otherwise impossible missions potentially feasible. A gram-scale spacecraft requires far less energy to accelerate than a ton-scale vessel, and the laser technology needed to propel such tiny craft, while still extraordinarily challenging, falls within the realm of achievable engineering rather than pure speculation. The mission architecture emerged from careful optimization studies. launch thousands of identical miniature probes rather than a single large spacecraft, accepting that many will fail but ensuring some reach the destination. Use ground-based or space-based lasers to push light sails attached to these probes, avoiding the need to carry propellant. Keep the spacecraft simple: cameras, basic sensors, minimal communication equipment, reducing both mass and complexity. Designed for a flyby mission rather than orbit insertion, eliminating the need for deceleration systems and dramatically reducing energy requirements. This pragmatic approach acknowledges current technological limitations while pushing boundaries where progress seems achievable. The project doesn't assume breakthrough physics or materials with impossible properties. Instead, it identifies what needs to improve: laser power, beam control, spacecraft miniaturization, sail materials, and assesses whether these improvements fall within plausible development trajectories. The timeline acknowledges that even with sustained effort and adequate funding, launching the first probes might take 20 to 30 years of development. Starshot energized the interstellar exploration community, demonstrating that serious people with serious resources were willing to invest in making such missions reality. The project sparked renewed interest in related technologies, encouraged new research directions, and showed that interstellar exploration might transition from distant dream to achievable goal within this century. Whether Starshot itself ultimately succeeds or not, it represents a crucial psychological and practical shift. Interstellar travel moving from someday, maybe, to here's how we might actually do it, and here's the funding to start trying. The probes envisioned by Breakthrough Starshot challenge every conventional notion of what a spacecraft should be. These starships would weigh mere grams and measure just centimeters across. Traditional spacecraft mass hundreds or thousands of kilograms, filled with redundant systems, shielding, power supplies, and propellant. The International Space Station weighs over 400 tons. Even small CubeSats, representing the cutting edge of miniaturization, typically mass several kilograms. Starshot proposes shrinking spacecraft by 3 to 4 orders of magnitude, creating devices that weigh less than a smartphone and measure roughly the size of a postage stamp. This extreme miniaturization becomes possible through aggressive simplification. A starship carries no propulsion system. The laser sail provides all thrust. No power generation beyond what tiny solar cells or capacitors can provide, just enough to operate during the brief flyby. No heavy shielding against radiation or impacts. The probe accepts that some systems may be damaged and relies on redundancy through numbers rather than robust individual units. The design philosophy accepts constraints that would doom conventional spacecraft, compensating through mass production and statistical probability rather than engineering perfection. The payload consists of only essential instruments. A camera, perhaps no larger than those in smartphones, captures images during the Proxima Centauri flyby. Basic spectrometers analyze light from the star and any planets encountered, determining atmospheric composition and surface properties. Simple magnetometers and particle detectors measure the local environment. The entire scientific package might weigh a single gram, using microelectronics technology adapted from consumer devices but hardened for the space environment. Communication systems present particular challenges at such small scales. Transmitting signals across 4 light-years requires either high power or large antennas, but the probe has neither. Starshot envisions using the light sail itself as a communication antenna, with embedded optical or radio frequency elements that can focus signals back toward Earth. The data rate would be extremely low, perhaps only a few bits per second, meaning that transmitting even a single high-resolution image might take days or weeks. The probe must prioritize what data to send, knowing it has limited opportunity to communicate its findings. Navigation and orientation systems must also fit within the mass budget. The probe needs to know its position, orientation, and velocity with sufficient accuracy to point its camera and communication system correctly during the brief encounter with Proxima Centauri. Tiny star trackers, accelerometers, and gyroscopes, adapted from smartphone technology but refined for space applications, provide this awareness. The onboard computer, operating on milliwatts of power, processes sensor data and executes pre-programmed commands without possibility of real-time updates from Earth. Manufacturing such devices requires pushing semiconductor fabrication and micro-electromechanical systems to their limits. Each starship essentially becomes a specialized integrated circuit with embedded sensors, minimal computation, and communication capabilities. Production would use techniques from the semiconductor industry, potentially fabricating multiple probes on single silicon wafers. This approach enables mass production, creating thousands of identical units at costs far below traditional spacecraft, where each vehicle represents a custom, hand-built artifact worth millions or billions of dollars. At 20% the speed of light, 60,000 kilometers per second. These diminutive probes would traverse the vast gulf to Proxima Centauri in approximately 20 years. This velocity represents a quantum leap beyond anything humanity has achieved. To put it in perspective, the fastest human-made object, the Parker Solar Probe during its closest solar approaches, reaches speeds around 200,000 kilometers per hour. Impressive until you realize that's only about 55 kilometers per second. At 60,000 kilometers per second, a probe would circle Earth's equator in less than a second and cross the distance from Earth to the Moon in just 6 seconds. Reaching such velocities requires extraordinary acceleration. The Starshot concept envisions laser arrays delivering power continuously for perhaps 10 to 15 minutes as the spacecraft recedes from Earth. During this brief window, the tiny probe must accelerate from essentially 0 to 20% light speed, an acceleration measured in tens of thousands of times Earth's gravity. No human could survive such forces, and even robust mechanical systems would struggle. Only because Starshot's probes weigh mere grams, with minimal internal complexity, can they potentially withstand the acceleration without disintegrating. The energy requirements prove staggering even for such lightweight craft. Accelerating a single gram to 20% light speed requires roughly 300 megajoules of kinetic energy, equivalent to the energy released by 70 kilograms of TNT explosive. For a spacecraft weighing even a few grams, you're talking about energy comparable to large conventional bombs, all delivered through laser light pressure over minutes. The laser array must maintain gigawatt-level power output throughout the acceleration phase, focusing this immense energy precisely on a sail, perhaps meters across, that's receding at rapidly increasing velocity. The acceleration phase presents numerous technical challenges beyond just power delivery. As the spacecraft accelerates, the Doppler effect shifts the laser light's wavelength from the probe's reference frame. The sail must maintain high reflectivity across this changing wavelength, or efficiency drops dramatically. The probe's attitude must remain stable. Any tumbling or misalignment means the sail doesn't catch the laser beam properly, reducing thrust or causing the craft to veer off course. Control systems must operate autonomously, because even at light speed, signals take increasingly long to travel between ground control and the receding probe. Once acceleration ends and the laser shuts off, the probe coasts at its final velocity for the entire journey. There's no mechanism for further speed changes, no fuel for course corrections, no way to slow down at arrival. The probe becomes a ballistic projectile, following whatever trajectory its acceleration phase established. Any errors in the initial aim or perturbations during acceleration cannot be corrected later. Navigation must be precise from the start because there are no second chances. This 20-year transit time to Proxima Centauri, while still longer than most human endeavors, falls within the realm of feasible mission planning. Scientists and engineers who work on the launch might still be active in their careers when data returns. The public attention span, notoriously fickle for long-duration projects, might maintain interest across 2 decades. Most importantly, the physics and engineering required, while extraordinarily challenging, don't violate known physical laws or require impossible materials. Space between the stars, while nearly empty, is not perfectly vacant, and at relativistic speeds, even the tiniest particles become deadly projectiles. The interstellar medium contains approximately 1 atom per cubic centimeter on average, mostly hydrogen, with traces of helium and heavier elements. In human terms, this represents a vacuum far more perfect than anything achievable in terrestrial laboratories. But for a spacecraft traveling at 60,000 kilometers per second, this tenuous gas becomes a sandblasting torrent, capable of destroying delicate instruments and eroding structural materials. The physics becomes sobering when you calculate impact energies. At 20% light speed, even a single hydrogen atom carries kinetic energy equivalent to a rifle bullet. A dust grain the size of a bacterium hits with the force of an exploding hand grenade. The Starship's journey to Proxima Centauri would involve countless such collisions, millions or billions of atomic impacts, thousands of dust grain strikes, and potentially dozens of encounters with larger debris. The damage mechanisms vary by particle size. Individual atoms and molecules penetrate surfaces, displacing atoms in the spacecraft's materials through collision cascades. Over time, this radiation damage degrades electronics, creates defects in structural materials, and clouds optical surfaces. The cumulative effect resembles accelerated aging. Materials that would last centuries in Earth orbit might fail within years when subjected to relativistic particle bombardment. Solar cells lose efficiency as their crystalline structure degrades. Computer chips develop bit errors as cosmic rays create charge in sensitive transistors. Larger particles cause catastrophic rather than cumulative damage. A dust grain striking the light sail punches clean through, leaving a hole that disrupts the sail's structural integrity and reduces its effective area. Multiple impacts gradually shred the gossamer membrane. If a particle strikes the spacecraft itself, the explosive impact vaporizes components, potentially destroying cameras, sensors, or communication systems instantly. The probe carries no shielding heavy enough to stop such projectiles. Adding protective mass would defeat the entire purpose of extreme miniaturization. Spacecraft designers have attempted to calculate collision probabilities along the route to Proxima Centauri. The interstellar medium's density varies, denser in some regions, more tenuous in others. Some trajectories might pass through dust clouds or the outskirts of nebulae, dramatically increasing impact risks. But even through relatively clear space, the probability of mission-ending collisions remains uncomfortably high for any individual probe. A single Starship might have only a 10 or 20% chance of surviving the journey intact. This statistical reality drives Starshot's strategy of launching thousands of probes rather than individual craft. If each probe has a 20% survival probability, launching 5,000 units means roughly 1,000 should reach Proxima Centauri functional. The approach accepts that most probes will fail, destroyed by impacts, damaged by radiation, or crippled by component failures. But even a 10% success rate yields hundreds of functional spacecraft at the destination, providing redundancy that ensures mission success despite individual losses. The strategy transforms the interstellar medium from an insurmountable barrier into a manageable statistical problem. Though one purchased at the cost of manufacturing and launching thousands of expendable vehicles. Breakthrough Starshot addresses the attrition problem not through heavily shielded individual craft, but through overwhelming numbers. The approach borrows from nature's strategy. Think of salmon spawning, where thousands of fish ensure that some survive to reproduce, or dandelion seeds scattered by wind, where mass distribution compensates for low individual success rates. Rather than investing enormous resources into making a single spacecraft robust enough to survive interstellar hazards, Starshot proposes manufacturing thousands of identical probes cheaply enough that losing most of them still leaves sufficient survivors to accomplish the mission. The economics of this strategy depend entirely on radical miniaturization and mass production. Traditional spacecraft cost millions or billions of dollars each because they're custom-built, one-of-a-kind vehicles. Every component undergoes extensive testing. Engineers design redundant systems to ensure mission success. Quality control operates at aerospace standards, where failure rates must approach zero. This painstaking approach makes sense for missions launching a single expensive craft, but becomes unnecessary when you're launching thousands. Starships could potentially be manufactured using techniques adapted from semiconductor fabrication. essentially treating spacecraft production like manufacturing computer chips. A single production run might create thousands of probes simultaneously, each identical to the others, with costs per unit dropping dramatically through economies of scale. If each probe costs thousands or tens of thousands of dollars rather than millions, losing 90% to interstellar hazards becomes economically acceptable. You simply launch more probes to compensate for expected losses. The statistical calculations become straightforward. If individual probe survival probability is 20%, you need 5 probes to expect 1 survivor. To ensure 10 survivors reach Proxima Centauri, launch 50 probes. For 100 survivors providing robust data redundancy, launch 500. The numbers scale linearly. Double the desired survivors, double the launch quantity. This predictability allows mission planners to adjust the fleet size based on budget constraints and scientific requirements. The approach also provides insurance against unknown hazards. Perhaps interstellar dust proves denser than current measurements suggest, or unexpected radiation fields damage electronics more severely than predicted. With a fleet of thousands, even if survival rates prove lower than hoped, enough probes should reach the destination to return valuable data. This resilience comes from spreading risk across many vehicles, rather than concentrating it in a few heavily engineered craft. Launch logistics favor this strategy as well. A mothership could carry thousands of gram-scale probes, releasing them sequentially as it orbits Earth. Each probe deploys its light sail, and ground-based lasers target them individually for acceleration. The staggered launches spread the laser array's workload over weeks or months, rather than requiring simultaneous acceleration of multiple craft. Different probes might take slightly different trajectories, sampling various paths through interstellar space and providing diverse scientific data even as many fail en route. This numbers-based approach transforms interstellar exploration from a single high-stakes mission into something resembling a fishing expedition. Cast a wide net, knowing many attempts will fail, but confident that some will succeed. The strategy accepts failure as inevitable, rather than something to be prevented at all costs, fundamentally changing how we think about deep space exploration. Sending tiny probes across interstellar distances solves only half the challenge. These spacecraft must also transmit their findings back across the cosmic void. Communication across 4 light-years pushes radio and optical technology to extreme limits. The signal must travel over 40 trillion kilometers, spreading and weakening according to the inverse square law. By the time a transmission from Proxima Centauri reaches Earth, the signal strength has diminished by a factor of roughly 1 followed by 28 zeros. Detecting such faint signals requires enormous receiving antennas and exquisitely sensitive receivers capable of distinguishing genuine data from background noise. The Starship's transmitter faces severe constraints. With only grams of mass available, the probe cannot carry large antennas or powerful transmitters. The entire communication system might draw only milliwatts of power, roughly what a hearing aid battery provides. Conventional radio communication under these constraints seems nearly impossible. The signal would be so weak that even Earth's largest radio telescopes might struggle to detect it against cosmic background radiation and interference from terrestrial sources. Starshot proposes using the light sail itself as a communication antenna, leveraging its relatively large surface area. By embedding optical or radio frequency elements into the sail's structure, engineers could create an antenna meters across without adding significant mass. The sail could reflect modulated laser light back toward Earth, creating an optical communication channel. Alternatively, radio transmitters could use the sail as a phased array, focusing radio waves into a narrow beam aimed at our solar system. Even with an optimized system, data rates would be extremely low. Transmitting a single high-resolution image, perhaps 10 megabytes of data, might require days or weeks at data rates measured in bits per second rather than megabits. Video would be impossible. The probe must prioritize ruthlessly, sending only the most scientifically valuable observations. Perhaps a few carefully selected images of Proxima b, spectroscopic data showing atmospheric composition, measurements of magnetic fields and particle radiation, the limited communication capacity constrains what science can be accomplished. Pointing accuracy becomes critical. The probe must aim its signal precisely at Earth across 4 light-years of distance. Even tiny angular errors mean the beam misses entirely, its precious data streaming uselessly into empty space. The spacecraft needs accurate knowledge of its position and Earth's location, accounting for the years of light travel time. Star trackers provide orientation reference, but the probe's computer must calculate where Earth will be when the signal arrives, compensating for orbital motion and the signal's finite speed. Receiving the signal on Earth requires dedicated facilities. Large radio telescope arrays like the Very Large Array or single-dish antennas like Arecibo could potentially detect transmissions if they're listening at the right frequency and pointing in the right direction. Optical receivers, large telescopes equipped with sensitive photon detectors, offer an alternative if the probe uses laser communication. Either approach demands sustained observation time and computational resources to extract weak signals from noise, essentially searching for needles in cosmic haystacks. Even at 20% light speed, the round-trip communication time to Proxima Centauri spans nearly a quarter-century, a delay that fundamentally changes the nature of exploration. Traditional space missions maintain real-time or near-real-time communication with mission control. Mars rovers face delays of 3 to 22 minutes depending on planetary positions, long enough to prevent joystick control but short enough for daily command sequences. Voyager 1, humanity's most distant probe, currently experiences light time delays of about 22 hours. But Proxima Centauri sits 4.2 light-years distant, meaning signals take 4.2 years to cross the gulf in either direction. This delay eliminates any possibility of real-time control or adaptive mission planning. When the probe reaches Proxima Centauri, 20 years will have passed since launch. The scientists and engineers who designed the mission will be 20 years older, some retired, some deceased, the entire team transformed by 2 decades of life. The political landscape will have shifted through multiple election cycles. Technology will have advanced dramatically. The computers used for mission planning will seem hopelessly obsolete. Yet the probe executes commands programmed years or decades earlier, operating according to plans made by people who may no longer even work in the field. The probe must function completely autonomously during its encounter with Proxima Centauri. Pre-programmed algorithms determine when to activate cameras, which targets to image, how to orient sensors, and what data to transmit. If something unexpected appears, an unanticipated moon, an unusual atmospheric phenomenon, evidence of something genuinely anomalous, the probe can only respond according to its pre-existing decision trees. There's no opportunity to radio Earth asking, "Should I look at this unusual feature?" and receive guidance. By the time Mission Control learns of the discovery, the probe will have passed the system and receded millions of kilometers beyond, its brief observation window closed forever. When the first signals finally arrive back at Earth, they'll reach a world 24 years older than the one that launched the mission. The data will be analyzed by scientists who were students or even children when the probes departed. The cultural context will have evolved. Perhaps public interest in space exploration waxed or waned, funding priorities shifted, or new discoveries elsewhere in astronomy changed what questions seem most important. Yet these delayed observations from a world 4 light-years away will still carry immense scientific value, answering questions posed a generation earlier. This temporal disconnect creates unique psychological and organizational challenges. How do you maintain institutional memory across such timescales? How do you preserve the data formats, communication protocols, and analysis tools needed to interpret signals arriving decades after launch? Space agencies must plan for multi-decade continuity, ensuring that future scientists will understand signals sent by spacecraft designed according to specifications written years before their careers began. The exploration becomes inherently multi-generational, not because the spacecraft carries multiple human generations, but because the mission timeline spans them. What awaits these probes at journey's end remains largely speculative. A planet orbiting a red dwarf star in ways that both tantalize and perplex astronomers. Proxima b circles its star at a distance of just 7.5 million kilometers, far closer than Mercury orbits our Sun. Yet Proxima Centauri is a red dwarf, much smaller and cooler than our Sun, with only about 12% of the Sun's mass and roughly 1/6 of 1% of its luminosity. At its close orbital distance, Proxima b receives approximately 65% of the stellar energy that Earth receives, placing it within the theoretical habitable zone where liquid water might exist on a planetary surface. The planet's mass, estimated at least 1.3 times Earth's, suggests a rocky composition rather than a gas giant. This raises the tantalizing possibility of a solid surface, continents and ocean basins, mountains and valleys, terrain that might vaguely resemble Earth's diverse geology. But the similarities likely end there. The orbital period of just 11.2 days means the planet races around its star at tremendous speeds, experiencing a year that lasts less than 2 Earth weeks. This rapid orbit, combined with the close proximity to its star, creates conditions radically different from our own planet's measured seasons and stable climate patterns. The stellar environment adds complexity to any speculation about habitability. Red dwarf stars are known for violent stellar activity, massive flares that can briefly double or triple the star's brightness, unleashing torrents of X-rays and ultraviolet radiation. Proxima Centauri exhibits such flares regularly, some so powerful they would bathe the planet in radiation doses thousands of times what Earth experiences from solar flares. These energetic events could strip away atmospheric gases over time, erode surface chemistry, and create conditions hostile to any life resembling what we know on Earth. Observations have attempted to detect an atmosphere around Proxima b, with mixed and inconclusive results. Some studies suggest the planet might have retained an atmosphere, despite the stellar bombardment, while others indicate it could be a barren rock, its gaseous envelope lost to space long ago. The uncertainty stems from the planet's size and distance. Even with our best telescopes, Proxima b remains a point of light whose properties must be inferred indirectly through subtle measurements of its star's motion and light. The magnetic field question remains equally mysterious. Earth's magnetic field shields our atmosphere from solar wind and protects surface life from harmful radiation. Does Proxima b generate a similar protective bubble? Red dwarf planets orbiting so close to their stars experience powerful magnetic interactions with stellar magnetic fields. These could either enhance a planetary magnetic field or suppress it entirely, with profound implications for atmospheric retention and surface conditions. What Starship probes might discover during their brief flyby could revolutionize our understanding of planetary habitability around red dwarf stars. Even if the planet proves sterile, a radiation-blasted rock stripped of atmosphere and water, the data would prove invaluable. We would learn how close-orbiting planets respond to the violent stellar environment of red dwarfs, the most common type of star in our galaxy, information crucial for understanding where life might arise elsewhere in the cosmos. Proxima b orbits so close to its star that it's almost certainly tidally locked, with one hemisphere perpetually facing the stellar fire while the other freezes in eternal darkness. Tidal locking occurs when gravitational forces synchronize a planet's rotation period with its orbital period, forcing the same face to always point toward the star. For planets orbiting very close to their stars, tidal locking happens relatively quickly in astronomical terms, perhaps within a few 100 million years. Given Proxima Centauri's age of roughly 4.8 billion years, Proxima b has had ample time to become tidally locked, trapped in this synchronized rotation. The consequences for planetary climate and habitability prove profound. The dayside hemisphere receives continuous stellar radiation, never experiencing night or temperature relief. Depending on atmospheric thickness and composition, dayside temperatures might reach hundreds of degrees, potentially hot enough to vaporize water and strip volatile compounds from exposed rock. The nightside, conversely, never receives direct starlight, cooling to extreme temperatures limited only by whatever heat the atmosphere can transport from the dayside. Without an atmosphere, nightside temperatures could plunge to near absolute zero, creating a world of extremes unimaginable on Earth. The terminator, the boundary between eternal day and eternal night, becomes perhaps the most interesting region. Here, the star hangs perpetually at the horizon, creating a twilight zone where temperatures might remain moderate. Some theoretical models suggest this region could harbour liquid water, even if both the day-side and night-side prove uninhabitable. Life, if it exists on tidally locked worlds, might concentrate in this narrow band where conditions remain tolerable, adapting to the perpetual twilight and the strange geometry of a sun that never rises or sets, but simply hangs motionless in the sky. Atmospheric dynamics on tidally locked planets differ radically from Earth's weather patterns. The extreme temperature gradient between dayside and nightside would drive powerful winds as hot air rises on the dayside and flows toward the nightside, cooling and descending before returning along the surface. These circulation patterns could theoretically transport enough heat to moderate temperatures across the planet, preventing the dayside from becoming too hot and the nightside from freezing completely. But the efficiency of this heat redistribution depends critically on atmospheric density and composition, factors we can only guess at currently. The perpetual day and endless night create strange possibilities for surface conditions. The dayside might feature vast deserts of baked rock, any water long since evaporated and transported to cooler regions. The nightside could be covered in ice kilometers thick, representing all the planet's water frozen out of the atmosphere and accumulated over billions of years. Or perhaps a thick atmosphere maintains temperature equilibrium, allowing liquid water across much of the surface despite the locked rotation. Tidal locking also affects magnetic field generation. Earth's magnetic field arises partly from the planet's rotation, driving convection in its liquid iron core. A tidally locked planet rotates much more slowly from an inertial reference frame, which might weaken or eliminate magnetic field generation entirely, leaving the planet vulnerable to stellar wind, stripping its atmosphere over geological timescales. Red dwarf stars like Proxima Centauri are notoriously temperamental, unleashing powerful flares that bathe their planets in intense radiation. These stellar outbursts occur when magnetic field lines in the star's atmosphere suddenly reconnect, releasing enormous amounts of stored magnetic energy in seconds or minutes. The energy manifests as intense bursts of X-rays, ultraviolet light, and charged particles that race outward from the star at near light speed. For Proxima Centauri, observations reveal flares occurring regularly, sometimes multiple events per day, with the largest ones briefly increasing the star's brightness by factors of 2 or 3. The proximity of Proxima b to its star amplifies the danger. Orbiting at just 7.5 million kilometers, the planet sits well within what would be considered the danger zone around a flare-active star. When a major flare erupts, Proxima b receives radiation doses thousands of times more intense than Earth experiences from even the most powerful solar storms. These events deliver not just visible light but hard X-rays and ultraviolet radiation capable of breaking chemical bonds in atmospheric molecules and surface materials. The charged particle component, protons and electrons accelerated to high energies, follows close behind, slamming into any atmosphere or exposed surface with devastating force. The cumulative effect of billions of years of such bombardment shapes the planet's evolution. Each flare strips away small amounts of atmospheric gas, the high-energy photons and particles giving atoms and molecules enough energy to escape the planet's gravity. Over geological time, this atmospheric erosion could remove substantial portions of whatever gases originally surrounded the planet. Venus and Mars both experienced atmospheric loss, but their losses occurred gradually over billions of years under relatively gentle solar wind. Proxima b faces far more violent conditions, potentially losing atmosphere orders of magnitude faster. Any potential life on Proxima b would need to contend with this hostile radiation environment. On Earth, our magnetic field and thick atmosphere shield surface life from most cosmic and solar radiation. Proxima b might lack such protection, forcing any biology to develop extreme radiation resistance or seek shelter underground or underwater. Microorganisms on Earth called extremophiles can survive remarkable radiation doses. Some bacteria can withstand thousands of times the radiation that kills humans. But even these hardy organisms might struggle under the relentless bombardment Proxima b experiences. The flares also create challenges for any spacecraft attempting to observe the planet. Starship probes arriving during a major flare event might have their sensitive electronics damaged or destroyed by the radiation pulse. Their cameras could be blinded by the intense light, their solar cells degraded by particle impacts, their computer memory corrupted by ionizing radiation. Mission planners cannot predict when flares will occur. Stellar activity follows patterns, but individual events remain essentially random. Some probes might arrive during quiet periods and capture excellent data, while others encounter the planet during violent storms that compromise their observations. These radiation storms represent one of many ways red dwarf stars differ from our Sun, challenging assumptions about habitability based on Earth-like conditions. Proxima b teaches us that the habitable zone defined purely by temperature tells only part of the story. Stellar behavior matters as much as distance when assessing whether worlds can support life. Whether Proxima b retains any atmosphere at all remains uncertain. The combination of tidal locking, stellar radiation, and its star's violent youth may have stripped away any gaseous envelope long ago. The question sits at the heart of the planet's habitability prospects. Without an atmosphere, Proxima b would be a barren rock, its surface exposed to the vacuum of space and the full fury of stellar radiation. Temperature extremes between day and night would be absolute, with no air to transport heat or moderate conditions. Water, if it ever existed, would either freeze solid on the night side or sublimate directly to vapor on the day side, escaping to space molecule by molecule. Detecting an atmosphere around such a distant planet proves extraordinarily difficult with current technology. Astronomers have attempted multiple approaches. Transit spectroscopy, which analyzes starlight filtering through a planet's atmosphere as it passes in front of its star, might reveal absorption signatures from atmospheric gases. But Proxima b's orbit doesn't necessarily align to produce transits visible from Earth, and even if it does, the signals would be incredibly faint. Other methods examine how stellar light reflects off the planet or look for thermal emission from the day side, but all require instruments at the very edge of current capabilities. Some observations have hinted at possible atmospheric signatures, but results remain ambiguous and contested. One study suggested the planet might have lost its atmosphere early in its history, when Proxima Centauri was younger and even more violently active. Young red dwarfs experience a prolonged period of intense magnetic activity and flare storms, potentially lasting hundreds of millions of years. Any planet forming around such a star would endure this hostile environment during its youth, when atmospheres remain vulnerable and planetary magnetic fields might not yet have fully developed. The atmospheric retention problem depends on multiple competing factors. Planet mass matters. More massive planets have stronger gravity that helps retain atmospheric gases against stellar wind stripping. Proxima b's mass, at least 1.3 Earth masses, provides some advantage. Magnetic fields, if present, create protective bubbles deflecting charged particles that would otherwise strip atmosphere directly. Atmospheric composition also plays a role. Lighter gases like hydrogen and helium escape more easily than heavier molecules like carbon dioxide or nitrogen. Theoretical models produce divergent predictions. Some calculations suggest Proxima b could have retained a thick atmosphere despite billions of years of stellar bombardment, particularly if it formed with abundant volatiles and developed a protective magnetic field. Other models indicate that red dwarf planets at such close orbital distances inevitably lose their atmospheres over geological time, regardless of initial conditions. The truth likely depends on details we cannot yet observe. The planet's precise mass, its internal structure and thermal evolution, the strength and geometry of any magnetic field, and the exact history of Proxima Centauri's activity. A definitive answer requires direct observation. Starship probes flying through the Proxima Centauri system could detect atmospheric presence through several methods. Observing how starlight scatters or refracts near the planet's limb would reveal whether gas surrounds the world. Even negative results, seeing a sharp, airless horizon, would provide valuable information, teaching us about atmospheric survival around the galaxy's most common type of star. Even if Proxima b proves entirely sterile, the scientific return from successfully reaching and studying it would be immeasurable. The search for extraterrestrial life drives much public enthusiasm for exoplanet exploration. But astrobiology represents only one of many profound questions that direct observation of Proxima b could answer. Understanding how planets form, evolve, and respond to their stellar environments remains fundamental to planetary science. Every new world we study adds crucial data points to our understanding of planetary diversity and the physical processes shaping rocky worlds throughout the universe. Proxima b offers a unique laboratory for studying planetary evolution around red dwarf stars, the most abundant type of star in our galaxy. Roughly 70% of all stars are red dwarfs, meaning that understanding planets in these systems tells us about the majority of potentially habitable real estate in the Milky Way. If red dwarf planets systematically lose their atmospheres or suffer sterilization from stellar flares, this dramatically reduces the number of worlds where life might arise. Conversely, if Proxima b retains a thick atmosphere and temperate conditions despite its hostile environment, billions of similar worlds throughout the galaxy might also remain habitable. The planet's geological history would provide invaluable information regardless of biological considerations. How does tidal locking affect a planet's internal heat engine and geological activity? Does the permanent day-night temperature gradient drive unusual tectonic patterns or volcanic activity? What happens to water distribution on a tidally locked world? Does it concentrate on the night side as ice, in equatorial regions as liquid, or escape to space entirely? These questions touch on fundamental planetary processes applicable to countless worlds beyond our solar system. Atmospheric science, if Proxima b retains an atmosphere, would benefit enormously from direct measurements. How do extreme temperature gradients between dayside and nightside drive circulation patterns? What chemical processes occur when one hemisphere receives continuous radiation while the other remains in perpetual darkness? Can photochemistry in the perpetual daylight create complex organic molecules even in the absence of life? Understanding atmospheric dynamics on tidally locked planets would inform our interpretation of observations from thousands of exoplanets discovered by missions like Kepler and TESS. The magnetic field question carries implications extending far beyond a single planet. If Proxima b generates a magnetic field despite slow rotation and possibly different internal structure than Earth, this would challenge our understanding of planetary dynamos. If it lacks a magnetic field, observing how stellar wind interacts directly with the atmosphere would provide unprecedented data on atmospheric stripping processes relevant to Mars, Venus, and countless exoplanets. Even the journey itself would yield transformative science. A functioning Starship probe, traveling through interstellar space for 20 years, would measure the interstellar medium's properties directly. Its density, composition, magnetic field structure, and particle environment. This data would refine our understanding of the material between stars and the conditions any future interstellar mission must navigate. The technological demonstrations alone, proving that gram-scale spacecraft can survive decades in space, that laser sail propulsion works at relativistic speeds, that communication across light years remains feasible, would open entirely new approaches to deep space exploration. Studying planetary formation and evolution in another star system provides context impossible to achieve by examining our solar system alone. Our solar system represents a single data point, one example of how planets form, migrate, and evolve around one particular type of star under one specific set of initial conditions. We've learned enormous amounts from studying the 8 planets, dozens of moons, and countless smaller bodies orbiting our Sun, but we cannot determine which features represent universal planetary processes and which are unique quirks of our particular system without comparing it to others. Proxima b offers our first opportunity for such comparison with data quality approaching what we have for solar system bodies. Distant exoplanets discovered by Kepler and other missions provide statistical information. We know their sizes, masses, and orbital parameters, but we observe them only as points of light or subtle variations in stellar brightness. We infer their properties indirectly, building models from limited data. A close flyby of Proxima b would deliver direct observations, actual images of the surface or cloud patterns, spectroscopic measurements of atmospheric composition, magnetic field readings, thermal maps showing temperature distribution. This data quality transforms our understanding from statistical inference to genuine geological and atmospheric science. The comparison would illuminate fundamental questions about terrestrial planet formation. Did Proxima b form in place at its current close orbit, or did it migrate inward from a more distant birthplace? The answer has implications for how rocky planets form around low-mass stars. Did it experience a late heavy bombardment similar to what Earth endured 4 billion years ago? Crater counting on any visible surface would provide clues. What role did water play in its formation and evolution? Detecting water ice, vapor, or evidence of past liquid water would constrain theories of volatile delivery and retention in close-orbiting planets. Comparing Proxima b to Earth reveals how different stellar environments shape planetary outcomes. Earth orbits a Sun-like G-type star at 1 astronomical unit, receiving relatively steady radiation with occasional modest solar storms. Proxima b orbits a red dwarf at 1/20th the distance, enduring violent flares and intense magnetic interactions. Both planets have similar masses and potentially rocky compositions, making them natural comparison subjects. Any differences in their atmospheres, surfaces, or magnetic fields can be attributed to the different stellar contexts rather than fundamental planetary characteristics. The comparison extends to understanding habitability itself. We don't know which of Earth's features are necessary for life and which are incidental. Does life require a large moon to stabilize axial tilt? Does life need plate tectonics to recycle carbon and maintain climate stability? Each difference teaches us something about the requirements of habitability. Beyond individual comparisons, Proxima b anchors what astronomers hope will become a well-studied sample of nearby exoplanets, gradually building a comprehensive understanding of how planets work throughout our galactic neighborhood. Carl Sagan observed that when humanity becomes ready to visit other stars, we will have fundamentally changed. The species attempting interstellar travel will differ profoundly from the one contemplating it today. This insight cuts deeper than mere technological readiness. Sagan understood that interstellar exploration demands more than advanced propulsion systems and miniaturized electronics. It requires a civilization capable of thinking across timescales that dwarf individual human lifespans. Cooperating internationally on projects whose benefits accrue to distant generations, and maintaining focus on goals that transcend immediate political or economic pressures. Consider what launching even a modest interstellar mission like Breakthrough Starshot actually demands. The laser array requires decades to design, test, and construct. International cooperation must persist across multiple political administrations and shifting geopolitical landscapes. Funding must flow consistently despite economic recessions, competing priorities, and the inevitable skepticism about investing billions in projects that produce no immediate returns. The scientists and engineers who begin such work understand they'll likely retire or die before witnessing success. This demands a cultural shift from our current emphasis on quarterly profits and election cycles toward genuine long-term thinking. The maturation extends beyond project management to fundamental values. A civilization ready for interstellar exploration has likely resolved or at least managed existential threats that currently preoccupy us. Climate change, nuclear proliferation, resource depletion, pandemic risks. Not because interstellar travel requires solving these problems technically, but because a species still struggling with self-inflicted existential risks lacks the stability and foresight necessary for multi-generational cosmic projects. You cannot plan missions spanning decades when your civilization might destabilize within years. Technological maturity represents only part of the equation. A spacefaring civilization must develop what might be called cosmic perspective, the ability to see humanity as one species sharing one planet in a vast universe, rather than as competing nations, religions, or ideologies. This doesn't require eliminating cultural diversity or imposing uniformity, but it does demand recognizing our common stake in survival and flourishing. The International Space Station, despite its limitations, demonstrated that former Cold War adversaries could cooperate on complex technological projects. Interstellar missions would require this cooperation elevated to unprecedented levels. The maturation also touches on humility and patience. Our current technological civilization is merely 4 centuries old, a blink in cosmic time. We've barely left Earth's immediate vicinity. Recognizing that interstellar exploration might require not just decades but centuries of development demands accepting our current limitations without abandoning ambition. A mature civilization balances optimism about future capabilities with realism about present constraints. Perhaps most fundamentally, the species that reaches other stars will have answered the question of whether short-lived intelligent beings can pursue goals transcending their individual existences. Can we build cathedrals knowing we'll never see their completion? Can we plant trees in whose shade we'll never sit? Can we launch spacecraft carrying messages we'll never hear answered? The very attempt to reach Proxima b, regardless of success or failure, forces us to confront these questions and, in confronting them, perhaps become the wiser species Sagan envisioned, one worthy of walking among the stars. The harsh reality remains that with our current understanding of physics and available technology, reaching Proxima b may never be truly possible. Yet this impossibility doesn't diminish the imperative to try. Throughout human history, we've confronted seemingly insurmountable barriers and attempted them anyway, not from delusion about our capabilities, but from understanding that the attempt itself transforms us. Medieval cathedral builders knew they wouldn't live to see their work completed, yet they laid foundations for structures that would take centuries to finish. The Apollo program pursued lunar landings when computers were less powerful than modern calculators and materials. Science couldn't guarantee crew survival. Each generation's impossible dream becomes the next generation's starting point. The technical challenges of reaching Proxima b, the energy requirements, the communication delays, the hostile interstellar environment, the sheer scale of cosmic distances, represent real physical constraints. Not merely engineering problems awaiting clever solutions. We may never develop propulsion systems capable of routine interstellar travel. The universe may have structured itself in ways that keep stellar civilizations permanently isolated, each confined to their home systems by the vast emptiness between stars. Physics might impose hard limits we cannot circumvent through any amount of ingenuity or determination. Yet attempting the journey serves purposes beyond arrival. The technologies developed for interstellar exploration, advanced materials, miniaturized electronics, powerful lasers, precision navigation systems, find applications throughout society. The international cooperation required to fund and execute such missions builds institutions and relationships that strengthen our collective capacity to address other civilizational challenges. The long-term thinking necessary for multi-decade or multi-century projects cultivates perspectives we desperately need for managing climate change, resource sustainability, and existential risks. More fundamentally, the attempt affirms something essential about human nature. This drive brought our ancestors out of Africa to populate every continent, across oceans to distant islands, and eventually off our planet entirely. Abandoning interstellar exploration because it seems impossible would mean accepting permanent confinement to our solar system. Declaring that our cosmic neighborhood extends no further than the Kuiper Belt, that our descendants will never witness alien sunrises or walk on worlds orbiting other stars. The attempt also confronts the Fermi paradox, the troubling silence we observe when searching for signs of other technological civilizations. Perhaps most species reach our level of development and then turn inward, concluding that interstellar space is too vast, too hostile, too expensive to bother with. Perhaps civilizations that accept this limitation eventually stagnate or self-destruct, while those that persist in attempting the impossible occasionally succeed and join some galactic community of explorers. We cannot know unless we try. Proxima b, with its tantalizing promise of a potentially habitable world orbiting our nearest stellar neighbor, represents more than a scientific curiosity or exploration target. It stands as a test of whether humanity can pursue goals transcending individual lifespans and immediate returns. Whether we succeed in reaching it or not, the attempt itself, the planning, the technology development, the international cooperation, the sustained commitment across generations, would demonstrate that we've matured enough as a species to think beyond ourselves, to invest in futures we'll never personally witness, to reach towards stars that may forever remain beyond our grasp but never beyond our imagination. And so we drift toward the end of our journey through the vast darkness separating us from Proxima b. We've explored the mathematics of impossibility, propulsion systems pushing physics to its limits, spacecraft measured in grams racing at 20% light speed, and the strange, tidally locked world that might await at journey's end. Radiation battered, yet tantalizing in its mysteries. The distances remain staggering. 4.2 light-years translates to 40 trillion kilometers of emptiness, a gulf so vast our fastest spacecraft would require tens of thousands of years to cross it. Even the most optimistic proposals demand decades of development, international cooperation on unprecedented scales, and technologies we've barely begun to imagine. Yet within this impossibility lies something profound about who we are. We are the species that looked at the moon and decided to walk there, the descendants of ancestors who crossed oceans not knowing what lay beyond the horizon. We carry the drive to reach beyond our grasp, to attempt the impossible because the attempt itself defines us. As you settle deeper into rest, feel gratitude for existing in this brief cosmic moment when we can contemplate such journeys. You are made of stardust, forged in ancient stellar furnaces, now conscious enough to wonder about other worlds circling distant suns. The atoms forming your body once drifted through interstellar space, travelling distances dwarfing anything we've discussed tonight. Whether we ever reach Proxima b, whether its planet harbours life or remains sterile, the universe has given us curiosity and the capacity to dream of distant shores. Rest now, knowing you are part of something vast and beautiful, a universe that created beings capable of looking up and asking, "What if?" Sleep well, cosmic traveller. The stars will still be there tomorrow.